Thank you. I really like the transition. Be prepared. We move from these lakes where we have plenty of life to these places which are far, far away, where we just don't know anything for now. This is what I'm going to tell you in the next 20 minutes. But since the transition is rather hard, I will take a few minutes to tell you where we are, because maybe you are not fully familiar to these places. On top left, you see Jupiter and the three large icy moons, which from left to right are Callisto, Ganymede, Europa, and then the fourth one, which is Io, is not an icy moon because there is no water on it. These moons are the Galilean moons. They are large because indeed they are very huge bodies. Callisto and Ganymede have a radius which is more than 2,500 kilometers. Ganymede itself, the second one, is bigger than Mercury. That's why we talk of giant icy moons. At the bottom of the slide, you see the moons which are around Saturn. Plenty of them. Only the two moons on which I will be focusing part of my talk are Titan, the orange one, which is a very big moon too. It is as large as Ganymede and Callisto. And the other one, which is a very small one, is Enceladus, that you can see on the left of the picture if you have good eyes. It is much, much smaller than the three giant moons at Jupiter and the Titan body, which is indeed very large. Talking of the environment, we are in the outer solar system, meaning that temperature is quite cold. At Jupiter, keep in your mind that the temperature at the surface is about 150 K, and at Saturn, we are at around 90 K when we deal with the temperature. So absolutely no way to have any life, organism, or whatever at the surface of these bodies. What we are going to do now is to go in the deep interiors of these moons in order to see what's going on in the deep interiors. And the reason why I'm here is that because we think that there are a lot of liquid water below the icy crust of these giant moons. Let's talk in one slide of what has been, about 10 years of discoveries. This slide summarizes very rapidly what has been discovered by the Galileo spacecraft about more than 10 years ago when it was in orbit in the Jupiter system. The first evidence that something was going on is certainly well described in the first slide that you see on the top left, where you see an infrared false color picture of the body, the surface of the Europa moon, where the blue stuff is pure ice. And what is surprising is that you see these huge cracks, lines, which are very red. And this red stuff is clearly not pure ice, but it is some kind of salt. Magnesium salt, sodium salt, maybe some clays. We don't know for sure. There is some complex chemistry going on, which comes from the deep interior, which has gone through the icy crust up to the surface. And this is, the scale of this picture is 1,000 kilometers. This is not just something which is very small. It is, imagine that the cracks at Europa are going through the entire surface, and this is a surface which has been cracked in many, many places at planetary scale. The real evidence that there are indeed liquid reservoirs in the deep interior of this moon comes from what you see on the right of the slide, where we see at the bottom Jupiter and the magnetic field of Jupiter, which is a very intense magnetic field. And what has been discovered by Margaret Kivelson and co-authors in 2004 and 2005 was that there was some kind of anomaly in the magnetic field when you go through the Europa moon. And this anomaly is due to the fact that there is an induced magnetic field. And this induced magnetic field can only be produced by the interaction between the magnetic field at Jupiter and some kind of electrical current which is produced below the icy crust at Europa. And this was, in fact, this was an hypothesis at that time, but it is now considered as a proof that there is a liquid layer below the icy crust, because the only way to produce the electrical current which produces the induced magnetic field that has been observed by Galileo is to have a liquid reservoir a few tens of kilometers below the icy crust. And finally, the geologic activity that you can see on the left at the bottom of the slide is another indication that something has been going on very recently in the past of this moon. And it is absolutely not a proof that there is a liquid layer, but this was, some kind of additional information. Some of you have certainly heard about this recent discovery 1 year ago when the Hubble Space Telescope has identified possibly a geyser activity, a plume activity in the South Pole at Europa I really insist on the possibly because there was only one observation which indicated that plume. Since then, we have had about 10 additional observations, which didn't find anything. And for the time being, we are absolutely not certain that the Europa moon is active and that this is not something, yes, which may be related to an auroral activity or whatever. So do not take that as a proof that there is a geyser activity like we have on other moons. This has not been proven. The only thing which is certain for now is that indeed we have liquid reservoirs. We have liquid oceans below the icy crust and on top of something which may be a silicate mantle on the icy moon, which is Europa. And just to give you an idea of the scale, we are talking of about 100 kilometer thick hydrosphere. The question is to know whether the liquid layer is below a few kilometers, as you can see on the left, or if the liquid layer is below a few tens of kilometers of icy crust. We just don't know about that, but we are certain that there is a liquid reservoir, a huge liquid reservoir below the crust. The other very well-known example is Enceladus. We are now in Saturn, and in Saturn, the Cassini spacecraft is still orbiting in the system, and it has identified a very active processes going on in the south pole of Enceladus. These active processes are geyser activity, and you can see at the bottom a 3D reconstruction of the many tens of geysers which are going in all directions along the 4 fractures which are called the tiger stripes, which are on the south pole of Enceladus, and which produce continuously ejection of material, which is liquid-rich material, water-rich material, which goes from the deep interior of Enceladus to the deep space. Once again, this is continuous activity. You can see the picture, which is on the right of the slide, which is one of the many Cassini observations of these active processes going on. You can see at the bottom that we are dealing with something which is what? Water-rich material with CO, CO2, CH4, some complex chemistry, the kind of chemistry that we find in cometary ices, and as we said this morning, not that complex, but still normal stuff with plenty of carbon, hydrogen, nitrogen, and sulfur. We think that, there are many models, but we think that this geyser activity is once again very probably related to existence of a deep liquid reservoir below the south pole. We don't know if this is a liquid ocean, that is, which is globally spread over the entire subsurface of the moon, or if it's something like the Lake Ontario or whatever, a huge lake which is below the south pole, but maybe not over the entire surface of the moon. We don't know about that, but there are strong evidences that there is some huge liquid reservoirs below the crust of this moon. Let's talk of the giant bodies now, Ganymede, Callisto, and Titan. These really big bodies have demonstrated also that there is most certainly liquid reservoirs below the crust. The picture that you see there is the one that we have for Ganymede, where once again the Galileo spacecraft has demonstrated that there is an induced magnetic field produced in addition to the intrinsic magnetic field, because this moon has a bipolar field as we have on Earth, and in addition to the Jovian field. This is the same for Callisto. We also have an induced magnetic field, and because of this, we are almost certain that there are liquid layers below the icy crust. Maybe some of you saw that picture, which has been which has been announced last week, and it is a Hubble observation of the auroral activity which is going on at Ganymede. Ganymede having an intrinsic magnetic field, so interaction with the Jovian field and with the solar wind produces periodic auroral activity, which are marvelous like this one. And the point is that the tilt of the auroral activity, the periodicity of this auroral activity is directly related to the existence and to the characteristics of the liquid layer. And what has been done by Joachim Sohr and colleagues this year is that from the models that they have produced, they have announced what should be the periodicity of the auroral activity, and what Hubble telescope has found is exactly what they have demonstrated in their model. And this is once again a strong evidence that there are indeed deep liquid reservoirs in the deep interior of these moons. As for Titan, I have no time to go into that, but for Titan, we think that there is a liquid ocean for other reasons. But we will come to that later on if you wish. The key issue for these giant moons, once again, Ganymede, Callisto, and Titan, is that we are in a totally different situation because we do not think that the liquid reservoir is in contact with the silicate mantle or whatever is in the inner core. The reason for that is that if you go and look at the phase diagram of pure water or any system which is rich, which is water rich, and if you imagine that we are dealing with an hydrosphere which allows the water to be at a few kilobars, something which does not occur on Earth. As soon as you are at the bottom of the ocean, you don't go above 1 kilobar. But in these places where we are dealing with an hydrosphere which may be 500 kilometers thick, in fact, the water-rich domain, the water-rich layer has a pressure at the bottom which is 4, 5, even 6 kilobars. And if you look at the phase diagram which is on the left, then you will see that above 2 kilobars, we do discover a new kind of high-pressure ices, a new kind of solid ices which do not exist on Earth, but which are very well known in the laboratory studies, which are called high-pressure ices. And as you can see, the temperature of these high-pressure ices can be much above 0 degrees. In fact, we have very high-pressure ices at very high temperatures. That's absolutely not the problem as long as you have high pressures. And so look at the red arrows that you can see in the picture on the right. Imagine that you go down from the surface through the hydrosphere from 0 kilometer down to 500 kilometers. This red arrow is reproduced on the left, and on the left you go through the phase diagram, and you are forced to increase the temperature first because we know that there is a liquid layer. You need to cross what we call the melting temperature of ice, and you go into the dark blue domain where we have liquid. And then you are forced to go almost vertically in a profile that we call a diabatic profile. This is physical law. We have no choice about that. You have to go almost vertically in the phase diagram, meaning that you are forced to cross again the high-pressure melting curves and to encounter a new ice. And that's why we call these liquid layers sandwich oceans. That's what we use in planetology. It is oceans that are in Ganymede, Titan, water-rich exoplanets, Callistos, are called sandwich oceans because they are supposed to be trapped in between the icy crust on top and a high-pressure icy layer at the bottom. All right. This is where we stand. Let's assume now that we have plenty of water reservoirs everywhere in the outer solar system as long as the moons are sufficiently big. And once again, this is mostly based on observations. This is one thing to consider these bodies as planetary objects. They are planetary objects in their own way, and they are strong interest. They have very strong interest for planetologists because they are planetary objects. To have an ocean is one thing. Then, since we have an ocean, we may be interested, of course, in dealing with the possible habitability of these oceans. This is another story. And let's go now into that, since you have 5 very good candidates for having habitable worlds. And let's be clear, it's too bad that Jean-Pierre is not there anymore. I am as he is. I mean, I'm really puzzled and never comfortable when we deal with habitability and habitable worlds. But I have a very clear understanding from my side about what it means, because as soon as something is habitable, we are going into trouble because of planetary protection issues for space mission. This has nothing to do with life. This has nothing, with extraterrestrial life. It has something to do with the fact that as soon as it is considered habitable, it means that you can bring some terrestrial life up there, and this may be in a perfectly viable, habitable environment and may reproduce by itself. So this is clearly something which is important for us. Habitability on my side means that we are in trouble with planetary protection issues. That's a summary, but it's how it works. So let's go. You know that, of course. Oh, already 5 minutes. Perfect. Perfect. No problem at all. I'm not going to go into that. I've already talked very briefly of liquid water. We know where we stand. Let's go through the essential elements, which is a key issue. And trust me when I say that chemical energy and stable environment are there. But our only problem is to know if we have enough complex chemistry in these places. Well, complex chemistry, I don't know how you call it, but from our side, the only complex chemistry we are dealing with is the one that we find in cometary ices. We have carbon, hydrogen, nitrogen, sulfur. We have some trouble to find phosphorus, clearly. But apart from that, as soon as we are in the outer solar system where there are plenty of ices, we are in a system where we have plenty of complex chemistry. Complex organics molecules are there everywhere. That's true. That's certainly not sufficient for having a habitable world. Otherwise, planetary protection for cometary mission should be 3 or 4. Of course, it's not because you have schnapps, sponge, or whatever that it means that you have potential for life. You need much more than that. In the case of Icy Satellites, we think that what is needed is to have strong exchange processes going on between the liquid and the silicates. Otherwise, you have not the capability to really talk of complex chemistry, the ones that we are dealing with when we talk with habitability. The key problem is that on the small moons, Enceladus and Europa, as you have heard just before, we consider for now, using a conservative approach, that they are indeed habitable because this complex chemistry is at hand. The liquid reservoir, if you remember well, is exactly should be in contact with the silicate layer, meaning that we have everything. The only problem that we have is that we are not certain for that. We need to do more studies in order to ensure that, because as long as you agree that you have CO2, CH4, CO, and so on, you agree with the fact that it's going to be very easy to produce compounds such as clatrate hydrates. And as soon as you produce clatrate hydrates, which are very, very stable, much more stable than pure ice, then you may end up with a liquid layer which is indeed not in full contact with the silicates, but which may be, above an hydrate layer, which may impede or in any way which may limit the exchange processes going on between the liquid layer and the silicate. I'm not saying that it works that way. I'm just saying that we just don't know how it is 100 kilometers below the icy crust of Europa, and this may be much more complicated than what we think. That being said, for the other moons, I will go the other way around. From what you have understood from the previous part, it is very clear that we should say that these moons are not habitable. There is no direct contact between the liquid layer and the silicates. Look at the picture on your left, and you see what 500 kilometers of high-pressure ice is between the liquid reservoir and the silicates. Full stop. But we may be wrong again, the other way around. We may be wrong because from those of you who are familiar with thermal convection and mantle convection in planetary, at a planetary scale, the way it goes on Earth, where we are dealing with a subsolidus convection, the Earth mantle is fully solid, but it moves a lot over millions of years. This is going to be the same way in these high-pressurized sea mantles. And because of this, we have a problem, which is illustrated here with this red circle. Because as soon as you agree that, and you have no choice, that there are convective motion in these bodies, the thermal boundary layer on top imposes that on top of the high-pressurized sea mantle, in fact, it should be liquid. In other words, there is a strong contradiction between what is this static model here and what is the dynamic model that we are forced to think of since we deal with a 500-kilometer thick ice. Once again, we do not have the solution about that, but it could be that this high-pressure icy layer is absolutely not solid high-pressure icy layer, but some kind of mushy material where exchange processes are going on through, a thermochemical convection where we have mixing, recrystallization, and this kind of stuff. Once again, we do not have the solution yet. Of course, all this is based on model. Remember that what we have at hand are the observation from the surface from a few flybys which were made by Galileo. But clearly, the models do not allow us to say once and for all that these bodies are habitable or are not habitable. We know that there is liquid water, we simply don't know what to do with it with respect to habitability. That's a question which is far from being solved. So in the next 2 minutes, I will end up with future missions and how we go from where we are to the questions of habitability and this kind of stuff. And I'm forced to come back to the list of 3 questions which are listed in the introduction of the program that you all have in front of you. In fact, space missions to the outer solar system are going to deal a little bit with these 2 last questions, which are the conditions under which life can exist, and does life exist elsewhere in the universe. Let me just go through this point. As I said before, this is a terrific table of planetary protection issues as listed by COSPAR, when I said just before that as soon as you agree that we are dealing with bodies where we have liquid reservoirs, in fact, when you do space mission, you are already thinking of what are the conditions under which life can exist. Because think of planetary protection, and we have already part of the answer here. Planetary protection should be considered, as a conservative approach, in the meaning that as soon as we send a planetary mission to these bodies, and as soon as we agree that there is some bacteria or anything there, is that we are able to go in the deep reservoirs, we think that life can exist in these places because it can proliferate since we are liquid reservoirs. I don't know what is the answer to that, but at least this is addressed by vital protection issues. Next mission, next two missions that we will see in the next 2 decades are these two, or at least, sorry, only one. That one is for certain. This is a JUICE mission which has been adopted by ESA in end of November 2014. This mission will be launched in 2022. We arrive in system in 2030. Take your time. But in any case, it will address a characterization. And by characterization, we mean indeed full characterization because this will be an orbiter of the Ganymede moon. And as to the question regarding the composition, regarding the physical characteristics of the liquid reservoir, and regarding to the exchange processes which are going on, especially at the high pressure layer, that will be certainly not be solved for all, but that will be addressed in full detail in 2050. As for the other one, this Europa Clipper mission, which is a NASA mission, or the one on your right is a NISA mission. I'm ready. The NASA mission, the Europa Clipper, is not yet selected. It may be decided in the next months, I don't know. And this is for launch in 2024. And this mission will only, or not only, but will be focused especially on the ocean that is under the icy crust at Europa. And of course, these two missions, since they are orbiter, clipper, or whatever that is doing science from remote, we address partially that question about the conditions under which life can exist, because they will characterize these putative habitats that we have under the icy crust of these moons. And my last slide is about the far future, about the question which is how does life exist elsewhere in the universe, as was said by Frances just before. We are not ready to send an electronic microscope on Mars. Well, this is worse in the outer solar system. We are absolutely not capable to send anything for the time being, which is capable to go through the icy crust, whichever its depth, its thickness is, which is going to go through the icy crust to the deep liquid layer, and then to do some kind of measurement, the one that you need in order to study this putative life which should be there. We simply are not capable of that. It is not part of the programmatic in space mission. I don't know if it will be done in the next 30, 40, 50 years, who knows, but this is not part of the study on which we are working on it. Thanks for your attention.